to verify, can people hear me at this level of volume in the very, very back? You're actually saying only sort of. You, with the next two, yeah. The person who looks really confused as to why I'm pointing at you? Yeah, that, yes. You seem like you were like going like this. Can you hear me?
I can hear you, but I don't want to speak for you.
That's perfect. Okay. Cool. All right. Okay. Hello. Is there any questions? All right, so I tend to come to this event and then try to figure out what I'm going to talk about often at the event. This time I actually came with a concept for what I wanted to talk about. The hardest part was figuring out what the title would be. And in fact, some of you I talked to you about potential titles, and in the end, I'm still just left bereft of feeling what I'm doing with the title. John has once again decided to put me as the last talk of the conference, so I also feel some aspect of responsibility of having a topic that tries to sum up one of the goals that people might have having come into an event like this. And so I think what brings people to actually come to a conference like this and to see, as John mentioned during his talk this morning, so many talks that also are not technical in nature or that are borderline between technical and non-technical. I think a lot of it is a drive for self-improvement, an attempt at figuring out how to be better at the trade that you are in. Now, so that's what I've got as a title, and we'll see if you actually believe that my topic, like the actual contents of my talk, lives up to this concept of this title. So I always like to start my talks, though, by quickly explaining who the hell am I? So, I'm Sork. Sorry, everyone online knows me as Sork. My name is Jay Freeman, but everyone online knows me as Sork. I speak every year at 360 iDev about random topics, sometimes technology. I've done talks on how to build computers out of nothing but magnets. I've given talks on just politics and history. I spent way too long last year talking about the fall of the Roman Empire. I developed Cydia, the alternative to the App Store for jailbroken iOS, which I think is ostensibly why I was invited to come to this conference in the first place back in 2008, 2009, when John was saying that he was, this morning when he was going online and finding anyone related to iPhone, and I was one of the people who came up, and he was poking me and trying me to come speak, and I was really happy and honored by that, by the way. So thank you so much, John, for having had me then and continuing to have me until today. And something that's actually kind of relevant for this talk. So I teach at the University of California, Santa Barbara College of Creative Studies, which is a weird little sub-program that I'm going to go into a little bit of depth on, I think. Yes, next slide, perfect. So the UCSB College of Creative Studies, there are 3 colleges at UCSB, one of which is Letters and Sciences, where they have all of the, there's a term for, I've forgotten the term for it, but like liberal arts, all the liberal arts type majors. And then there's the College of Engineering, where you've got all of the computer science, computer engineering, hardware, et cetera. Each of those has about 10,000 students. The College of Creative Studies only has 350 students. I attended the College of Creative Studies. I was recruited to it, and I essentially never left. And I don't, by the way, officially, I mean, sometimes I do actually, but I don't really officially teach there. I just kind of hang out there and continue to co-teach the introductory classes with the person who's ostensibly supposed to be running it. And occasionally they will hire me every few years or so to teach a more advanced course. Now, this is a program, some people are like, is this an honors program? And no, we all agree that it's not called an honors program, because that's where you take somebody who's bored and you give them a bunch of extra work on top of what they were supposed to be doing, and hopefully they do all of the extra work. In practice, what a CCS student does is they just fail the class because they don't do any of the original work, and what they end up doing, I should say, is highly motivated students is one of the big things for it. But they don't do any of the original work. They do all of the honors work, but then they still manage to fail the class. I had a friend who was in the College of Engineering who essentially was doing all of the homework for the people who were 2 years ahead of him, and failing out of his classes, and he ended up failing out of the whole university. And he really should have been a CCS student. They just describe themselves as a graduate school for undergraduates. I hate that description, and the reason why is that in a graduate program, you have to decide what you want to do. You work on doing that, and if it turns out that it's a dead end, you're screwed. I mean, now what? So you have to figure out how to rescue your research in order to try to continue. In an undergraduate program, you learn something, you get your degree, and you move on. I describe it semi-awkwardly as a special education program for creatives. So you look up in special education, there's a wide variety of things. People with, for example, ADHD, you would still count that as like a special education program. The kind of person who is oftentimes a CCS student is the kind of person who, like me, I got perfect math SAT score. I got a 5 in AP tests. But I was in the bottom half of my class, and my guidance counselor thought that I was a travesty that would not get into any college ever. And I got recruited to this program because they were like, we're going to try to essentially figure out ways of fixing education to try to help people like this. And I probably would have failed out of any other program. And I mean, just trying to get descriptions for talks, for conferences like this, John probably is driven crazy continually by the fact that I don't give him anything. And that even when I start thinking about it, I end up in this like anxiety, panic disorder, trying to figure out how to actually get him something on some reasonable time frame. And if it weren't for a program like this, I think I'd be screwed. The person who constructed it kind of called it, I wanted to think of it as like the campus living room, a place where you could get a lot of people together in order to talk about interesting topics. And it was something that was constructed in the 60s, but we like to say that it was not of the 60s because it was actually it wasn't a lot of touchy-feeliness, it was a lot of heavy, hardcore researchness. So is it interdisciplinary? Is it when you call it creative studies, it makes you think that you're going to learn a lot of different separate things? And the answer there is no. There are 8 majors, and you're supposed to learn one of them. And you're supposed to choose one. You can actually do a major, but you go deep into each. It's not that the classes are designed to cross between them. And these are like core majors, things like physics, biology, chemistry, mathematics. Awkwardly, they've renamed it to computing for weird like, there's a term I'm also missing here, but it's a credential-related reasons that it's just, and they chose a bad name for it, but whatever. Each of these was designed to be something that an undergraduate could push the state of the art in before they left the university. And the person who founded the college, and this is kind of why I'm going through a lot of this study, to show that I care about education, that I have an opportunity to work with a lot of people at their introduction at the beginning of their education, but also that I've been steeped in a premise that Marvin Mudrick, the person who created this college, felt that the reason why it wasn't the College of General Studies, it was the College of Creative Studies, it wasn't an interdisciplinary program, it was 8 core majors that you went deep into, was that if you could learn one thing really, really well, now you know what it means to know something. And you will no longer fool yourself into believing that you know other things. You will no longer go into something else and not understand where along the progress bar you are of getting to understanding, and you might have tools to get you to where you will go. And these, of course, these are general principles that you hear a lot about just education, any university for. But I think that there's something that Mudrick really spent time thinking through the specific detail. So now, having sat in that system, I will then say, I said academia actually has value. And this is maybe a controversial comment because a lot of people are like, oh, academia is just really stupid and it's pointless. But I'm going to redefine here. Academia is not a place or a service. Academia is a thought process. It's not necessarily something that you pay for in order to go and spend 4 years at. It's a way of thinking about a problem such that you are attempting to learn something about a deep topic, and you're trying to learn what is essentially at both the state of the art and trying to push the boundary, and then provide that research back to other people in the form of publishing that work so that other people can experience it. And I think there are a lot of people who succeed in cobbling together something that feels a lot like a university system that I would feel is very academic, but they're doing it inside of a research program at a large company, or they're doing it within an open source community. But the thing that I think that the structured programs can do, but you don't have to go to the structured program to get, is to try to minimize the number of holes that you are left with at the end. This is actually something that I've even experienced as a College of Creative Studies student. People in the College of Engineering, one professor in particular, just felt that the College of Creative Studies program left people with holes in their knowledge, and that we had too much lenience in how we took courses and in what order we did them in order to deal with all of our paperwork issues, and that people would leave without having a strong enough knowledge in architecture or in compilers. So I will say, I think there's a lot of value, I think, in studying algorithms. I think people sometimes will think, oh, okay, well, as long as I get the job done, it's fine. At some point, when you get a good number of users and you have to start thinking about the scalability of your system, it's not a low-level problem. It's oftentimes like, I think people think about optimization and they think about it in terms of, well, I'll drop to a lower-level programming language and I'll figure out how to like eke out every individual nanosecond of time I've got from my computer. It's oftentimes the extremely high-level thoughts of, if I want to put things in an order, I can do it with a selection sort, I can do it with an insertion sort, I can do it with a quick sort, I can do it with a merge sort, and it's not just sorting algorithms, it's all sorts of things. I find myself in my work on databases, when I'm using databases, I find myself often thinking about the algorithms that I know that the database must be using in order to accomplish the tasks that I'm working on. And that informs me into what kind of index structures I should be using in order to fix the problem I'm running into, as opposed to throwing more layers of abstraction or caching or something that only sort of try to fix the problem. Possibly 3 lines of code later, I can truly fix the problem. I think it matters a lot to analyze protocols and to think through what it really means when you have people, like, well, people is one way, but computer systems that are divided into parts. There's an entire area of focus on distributed computing and parallel computing, and thinking about that, I think, is something that, and learning about the parts of that is something that's, I think, very important when we're building networked systems, and you find yourself in experiencing network failures. The 10 fallacies of, maybe it's 8 fallacies. There's a number of fallacies of network computing that I highly recommend reading. It was a paper from, I believe, the 80s, if not, maybe it was early 90s, and looking at things like the network will fail, or that latency does exist, and things, and really trying to appreciate what those mean for you. I think that it's very important to try to understand the hardware you're working with, because I think that has ramifications on what you're able to build. And this is actually a talk I gave here now it's maybe even 4 years ago, on how to build a computer out of magnets. You can actually find it in the 360 iDev archives, but the title is useless. So maybe search for Jay Freeman and look for diagrams. Now, I was mentioning earlier about micro-optimizations, but I think there actually is something then to understand about where latency comes from. And so Admiral Grace Hopper, she was one of the first programmers of the, I forgot what computer, but it was one of the first computers. She gave a talk at one point. You can actually find the small YouTube video of this, but one of the core aspects of it is that she wanted to physically demonstrate what a nanosecond was. And she said that a nanosecond is 11.8 inches long, the maximum limiting distance that electricity can travel in a billionth of a second. At the end of a week, so she had asked the engineering department to give her that length of wire. At the end of about a week, I call back and say I need something to compare this to. Here's a microsecond that she holds up this massive coil, 948 feet. I sometimes think we should hang one over every programmer's desk or around their neck so they know what they're throwing away when they throw away a microsecond. An admiral wanted to know why it took so damn long to send a message via satellite, and I had to point out that between here and the satellite, there was a very large number of nanoseconds. Memory and latency. So computers essentially are built on lots of a towering stack of abstractions, each one of which is a caching layer for the pieces below it. And an understanding of that actually is weirdly important for being able to build systems that are correct in the memory models of our current programming languages. It's not even just a matter of performance, it's often a matter of correctness. When it is a matter of performance, it is often a matter of dire performance. And I recommend learning about things like the L1 cache, L2 cache, L3 cache. One thing I might point out about this, it's just kind of a quick little inspiring story, is the idea that if you think about memory on your computer, if you access something that is in a register, it is almost like having a sheet of paper on your desk with a word written on it that you're looking at. If you're accessing something, or actually maybe even, it's like something that's almost in your head. But as you go down the memory hierarchy, it's like if you look at like L1 cache, it's like you've got a book on your desk, you're gonna have to open up and flip through to actually find something. You go to L2 cache, it's like I'm gonna go walk across the room to my bookshelf, find a book, pull it off, go back to my desk, open it up and find something. You go to L3 cache, and it's like, okay, I guess I'm gonna drive down the street to the library and go find a book. And then you get to the point of saying something like, now I'm gonna go to disk, because it got swapped to disk. Okay, I'm gonna get on a boat, and I'm going to go overseas, and I'm going to go get something from a library, and then get back on a boat and head back. Like the change between those is so drastic that it leads to counterintuitive things, like if you store something on a computer over the network, it might be faster to access than storing something on the local disk drive because the disk is so slow. So I then think about, there are a lot of people think about coding boot camps, and I have a weird opinion of these because I think that I think that these offer value, but I'm also concerned that they offer that value and then do it at the expense of saying that you don't need to learn everything else. It's not, or that the learning the other things is useless. And I think I think it's great that you can learn things in a different order and you can decide that, well, I really care about the craft of doing this right now and I want to experience this. But I think you really should go back and learn those other topics. And I will also then say that it's never too late to get involved in this, either in this industry in general or to learn any of these topics. I pointed a few people, one of whom I work with, his name is Brian Fox. He wrote Bash, Readline, Tech Info, Wells Fargo Online Banking. He did not grow up with computers, he did not grow up with much of anything. And then he was only after he came and was living near a college, and he started hanging out there and met people like Marvin Minsky, and started asking, like, what are you doing? He ended up getting just an internship job at the college while he learned to program, and is now one of the very influential people at the core of open source software, and he wrote software that you were probably using every single day. I say Wells Fargo Online Banking, that was the first online banking system. He ended up building that. Yehuda Katz, somebody maybe is more familiar to some modern programmers, he wrote MERB. He was on the jQuery plugin team. He wrote Ruby on, he was on the core of Ruby on Rails after they merged MERB. He wrote Ember.js, and now he's on the standardization committee for ECMAScript, and he's in the core Rust team. Yehuda is somebody who, he went to college, I don't remember what it was for, but it was for something totally non-engineering related, and then it was someone who's decided that, you know what, computer science seems important, and he decided to start learning it, and suddenly started falling into all of these interesting and important jobs and tasks. All right, so one of the classes that I teach at UCSB, at CCS, when I do get hired, is something I call comparative machine language morphology. And this is where maybe I can provide some more interesting technical content for this talk for a little while. This is a title that sounds very much like a course in linguistics, and that's actually kind of, I spent way too much of my time in grad school learning linguistics and then really not getting anywhere in my computer science degree and just causing the College of Engineering to really, really hate me. I went into grad school in the College of Engineering after I graduated from CCS, and I did not do that well. So a weirdly stereotypical linguist for me is Daniel Jackson from Stargate SG-1. This might be an age group that actually knows about Stargate SG-1. I oftentimes talk in my jailbreak community to age groups who look at me with blank eyes because they've never even heard of Stargate at all. But so in Stargate SG-1, in Stargate also in the movie, there was a character, Daniel Jackson, who was a linguist, who was a person who had figured out a lot of the symbology that was used in order to make all the Stargates connect together. And he would do this thing where it's like in the first episode of the television show, they run across some alien species, and he starts trying to talk to them, and he's like, I think I'm understanding this. Like they're talking about they're choosing something, and he goes back and he's like, it's a derivation of Arabic combined with, and the commander just cuts him off. And he's like, yeah, all right, whatever. Just ask him to take us to the nearest villager town. And there's no particular interest in how or why Daniel knows these things. Not that that's necessarily a problem at the level of what the commander's doing. But what Daniel was doing, right, is something that's not even that far-fetched. If you know a lot of languages and you're able to kind of cross the boundaries of all of them, can you figure out what somebody is saying? And so it's when Swift was released in 2014, I was in the audience at WWDC, and I was watching the keynote presentation, and I was seeing just a few slides worth of it, and I'm like, wait, I think I get this. This is like OCaml, but it's got the error handling from Haskell, but they had to add extra syntax for it because they didn't actually, integrate any kind of monadic layer for that. But they've got syntax that feels a little bit more like Scala, but if you were to try to do it as a Ruby programmer, I think I can program in this. And I did the same thing to the AltConf people, where I had a talk 3 days later across the street where I had not given them a title or a description or anything, and I went over there and I'm like, I want to do a talk on advanced implementation details of Swift. Like, and that was just that announced? Yes. It's like, okay. And I did that. And I was kind of going through like how the memory models work, and I was sitting there like crashing the compiler constantly with like advanced cases and in the coding labs. And I think that's something that's teachable quickly, which is why, as I say, like when I give this as a class at an undergrad level, and like people take it their first year sometimes, and I go over lots of different programming languages. And and I think one of the kind of skill sets that gives you is also an ability to kind of judge languages. So there's this great article, I recommend reading through it. I'm sadly I'm going to give you enough of this that hopefully it doesn't feel like I've ruined the punchline, because you probably aren't going to read it anyway. It's an article that goes through Go, comparing it to brand X in the way that old commercials would say, we're going to compare your detergent to brand X. And then at the end, they do this big reveal, right? And so they go through and they show all these different kinds of syntax examples and show that there are places where Go seems a little bit better and places where brand X seems a little bit better. They're looking at like things like consistency of form versus ease of use. And it's interesting because brand X is actually quite competitive with Go. And there's some places where the ergonomics of brand X seem a little bit strange, but honestly, there were a lot of places where Go felt a little bit strange too. And at the end, they point out that brand X is Algol 68. And it's like, could we have just taken Algol 68 and made some improvements to it and like added a little bit of the Go channel infrastructure and gone Go routines or something? Like, it's just like, do we really need to have been constructing some of these new systems in these ways? And I think that you also, this ability to like look at languages and kind of feel like the extent to which they're valuable and the extent to which they're not can be important. So I encourage people to explore languages, and I'm going to kind of go through a few here. I'm going to say, as this is from 1997, which is context that apparently is very important to understand when they say Northern California, which Northern California they mean. But Mary Schmick wrote an advice column, Advice Like Youth, Probably Just Wasted on the Young, which you may have heard this in the form of the Sunscreen song. But live in New York once, but leave it before it makes you hard. Live in Northern California once, but leave before it makes you soft. Travel. So in a similar form, small talk. Learn small talk until you feel like you truly understand object-oriented programming. Now, I say that in that way because I think a lot of people might think, oh, object-oriented programming, I know Java. You do not know object-oriented programming. Java was this really weird bastardization of the entire thought process that ended up having to lead to most of the design patterns that you see are attempts at figuring out how to fix issues in Java in order to actually accomplish very basic programming patterns. You do know maybe languages that are kind of okay. Weirdly, Objective-C is they've based a lot on small talk. Ruby has got a lot of small talk in it, but there's something really interesting about small talk, which is that, so in Objective-C, you already have this experience that classes are pretty much objects. I mean, they're weirdly not, in the sense that if you try to just make an ID variable and assign NSObject to it, it won't work. But there is an object for NSObject. If you do NSObject class, you will get the class object for NSObject, which is this meta object for what NSObject is, right? If you do but the way you allocate it, it's not like there's a new keyword in the language. It's not that there is a mechanism in the language to allocate something. You just send a message to the NSObject class and ask it to allocate itself, and it gives you back this thing. Smalltalk did that for everything. Like, there isn't like an if statement, right? So it's like if Objective-C or you see, Java is so generic at this point. You've got if statements where you've got this like if, and then you put a little test inside of there, and then you've got two code blocks that are separated by this else keyword, and the parser knows about this concept. Imagine if, and this is like Objective-C syntax, if you were to take your Boolean, do the little Objective-C casty thing to it in order to get an NS Boolean, and then had added a selector to NS Boolean that takes two blocks for the true case and the false case. Now you don't need an if statement anymore. You might want a compiler optimization to make this run faster, but you don't need an if statement anymore. This is small talk, is they've just dropped more of this stuff around it because they use periods as their statement finalizers, and then they don't need the bracket syntax because they weren't escaping out of C at the beginning. They were just starting from this premise in the first place. And so this is how you do an if statement in small talk. This is how you do a while statement in small talk, is you take a block and you pass it, you send it the while true message, and you pass that another block. And everything in the language, the way that you add methods to a class is you send a message to the class with the code for the message that you are going implementation for it. It's not like there's a runtime you have in Objective-C where you're manipulating the objects. No. The classes are what are manipulating themselves, and they're providing all the code dispatching. Another little fun detail about small talk is you'll notice weird characters. They had a different keyboard than you do. And over time, it was simply believed that it was easier to just memorize the new characters than it was to fix the rendering. But the caret key is really, it's return, and that's supposed to be an up arrow. And the underscore key that you weirdly use for assigning variables, and you're like, why would they do this? That used to render as a left arrow. And in fact, if you're in like a small talk environment, it'll oftentimes will render like that. Everything in small talk then is object-oriented, and it provides the debugger as part of the interface. If you're in the graphical interface for it, you can inspect into anything, pull up the debugger on it, and then start manipulating the objects and sending messages to your running instances of all your programs. Lisp. Learn enough Lisp until you can understand the benefit of homoiconic languages. So here's an example of Fibonacci written in C. And I just chose int arbitrarily, whatever. But so you've got again structured statements. We've got specialized syntax for our expressions, our math expressions. We've got this concept of return that is operating within the scope of these block constructs. This is something that, if you want to manipulate it, if you would like to parse it, you are at well, thankfully we now have libclang, so now you can go through and actually try to get some kind of object representation of your code base, but that's something that now is it's a very complicated interface, and I've tried to use it at various points, and it's surprising actually how complicated libclang is to actually be able to get all the structure that you might want from all the little subparts of all these things, particularly when people start adding more and more syntax in specific compilers and make modifications to it. Let's look at something that's a little bit simpler. Here's Python. People oftentimes say Python looks a lot like pseudocode. I mean, Python just looks a lot like the C code, I mean, in some sense. I mean, it's just, when you start, I do this thing actually where I've got like 22 different languages in the comparative machine morphology class, and I've got like the same code that I wrote that's like a small object-oriented example. Not even all of the languages are object-oriented, and I've just aligned all of the code such that you can flip back and forth between all of the languages, and the only thing that changes are the keywords, and all of the constants stay the same. And it's amazing, like how much is just the same across all languages. And you'll come across an occasional language like OCaml, and just all of it disappears except for like a small handful of identifiers. And you'll come across a language like Ada, and it's just like the screen is just dense with text. But Lisp decides to have a very similar structure, but what it does is it unifies everything into essentially, you think like maybe like a function call. And so they put the function name inside of the parentheses. And so here we've got essentially a function that we're calling. It's not actually a function, but it's essentially like, right, I'm saying essentially a function we're calling def on to define a function. We're passing it the name of the function, a list of its arguments, and then we've got the code for it, which is now an if statement, which is itself, if is kind of like maybe sort of like a function or something that takes as an argument a test. And then two values that will return one or the other. It's more like a ternary condition operator, like question equals. And in this language, this structure is something that is universal. Everything looks like this. You've got this kind of identifier that's defining what it's doing at the beginning, and then you've got a set of items that come after it. It forms lists. It's almost like if you had taken, the downside of this course is you'll notice at the end here, the increasingly large number of parentheses, and the complaint you'll oftentimes hear about Lisp is that you essentially just hold down the parenthesis key and you start getting errors from your IDE. So the thing that's neat about this is it kind of gives you the ability to do things like select star from code or expression-like, because now your code is a trivial to parse data format, and is in fact the same data format you would use if you wanted to have an inline array. Like our list of arguments is not where the first element is special. It's not a function name. It was just a list of arguments. But everything is just a list. So then we've got a list of our code, which would be, if I had multiple statements here, would just have been separate parentheses groups items inside of the def-on area. It maybe like if you had your code and you try to store it as XML, which you probably hate, if nothing else, it's 2019, so it's like I've said a dirty word here. It's like maybe if you try to store your code as JSON or something, and everything was designed to like be little JSON objects that were going through. People have tried to do stuff like this, but Lisp is like that, and what it lets you do is all of these things where you've got compile time code generation or binding, where you've got tools that sit outside of your language and are attempting to build little one-off code generation, and you've got to figure out now how to integrate them into your build environment, get them to run in the right order. Like I think a lot of people get, like they start thinking about, well, if I start manipulating my code, who knows what's going to happen now, because I'm going to end up, it's going to be so confusing to understand. But is it really that much different than what you're currently doing when you've got some arbitrary little domain-specific language that you've cobbled out of selectors in Objective-C, such that it's like, well, I'm reading something that is now like, has all sorts of names that aren't quite what I'm used to having. I've got to learn that whole library. Is that different from when you're using the C preprocessor in order to do something with repetitive code in the most horrible way possible with extra little parentheses to try to avoid all the little preprocessing issues? When you're using generics or templates in a language like C++ or even something like Java or C#, where you're essentially expanding multiple copies of the same code with, over different types, SQL model binding. Or IDL generation, where you've got something where you've defined what your schema is, and then a bunch of boilerplate code gets generated for you. Declarative user interface. This is another example where you had something that was a data structure and is generating a bunch of code. And if that step were something that were available during the same compile steps as everything else, there actually is a lot of argument that it makes things easier. Now, I'll say some people may have learned Clojure, and I'm going to give you a warning about it. There is although I can try to patch it right now, there is a core piece of beauty in Lisp, which if you start learning about how you manipulate all the code base, there's this thing where they call it quoting, where you take a list of code and you don't run it, you just experience the code. You've got unquoting, where you take a list of code and you expand it back as code, and you'll notice that the open quotation mark and the comma are an inverted of each other. And then there's this thing called quasi-quote, which is kind of like an apostrophe, but kinked to the side a little bit. Clojure decided to use comma to represent list separation, but they didn't need it because Lisp doesn't have list separation, and so they used comma as white space. It literally means nothing to the parser. And so they then had to add, I think it was like an @ sign. I actually don't remember now right now. It might have been a pound sign. I think it was an @ sign for unquote. And it no longer has this beauty of the quote unquote that you see as you are iterating the code. And Clojure also decided to not support reader macros, but there's a cool hack you can install in order to get them from a third party. Haskell. Learn enough Haskell to know what a monad is. This is hard, okay? And I'll start by saying that, because you're trying to read online what a monad is, and people are going to be like, well, monads are burritos. And it's just like, I'm a strong believer in the monad tutorial fallacy, okay? So the monad tutorial fallacy consists in failing to recognize the critical role that struggling through fundamental details plays in the building of tuition. This, I suspect, is also one of the things that separates good teachers from poor ones. If you ever find yourself frustrated and astounded that someone else does not grasp a concept as easily and intuitively as you do, even after you clearly explain your intuition to them, look, it's really quite simple, you say, then you are suffering from the monad tutorial fallacy. So that said, it's really quite simple, I say. But what I'm going to try to give you is not understanding of them. I'm just going to try to give you an inspiration for why you should learn them and struggle through them. And I think that's what separates what I'm about to try to do from the monad tutorial fallacy. So if you think of a semicolon as a statement terminator, as you might in C or Objective-C, C++, Java, some languages use it as a statement separator, where you merely have like a list of statements that are separated in the way you might have a list of array elements separated by commas. Imagine if you had the ability to have an overloaded semicolon operator in your programming language that took the code that was just run on the left-hand side of the semicolon and all of the code that has yet to run on the right-hand side of the semicolon and had the opportunity to do something with that. What could you do with that? If you could take a function and say this is operating within this semicolon the semicolon overrode namespace. So Haskell starts off with the most hard one you could possibly imagine, I/O and side effects. So we're just going to skip that. So the simplest thing you might imagine is null coalescing. So if you've got an expression on the left that might return an object, might return null, and you've got a bunch of code that hasn't operated on the right yet that will take that result as an argument, if it's null, you could just skip all of it, or if it's not null, you could call it. That's like, a trivial if statement now inside of your overloaded semicolon operator. Errors and exceptions. If you've got code on the right that might either work or throw an exception, and you've got code on the left that hasn't happened yet, if the code on the did I say the left? I was actually purposefully doing it so that it was from your direction, and then I was using my words. So if you've got code on the left, which might throw an exception or might work, and you've got code on the right that hasn't happened yet, you could take the code on the left and only run the code on the right if it worked. Otherwise, return the exception with an indicator that tells the overloaded semicolon that is occurring before it to keep returning until there's a catch. State threading. You've got something like a thread local storage that you want to thread through a bunch of code. But what you could do is you could just pass that as an extra argument to every single function call by making it so that everything returns two values and then just chain it through in the semicolon operator. So it's just like you've got this like secret back channel that you can use to get information through. List comprehensions. If you've got code that is running on the left that returns an array, and you've got code on the right that only works on one element, you can make the whole thing return an entire array by simply running the code on the right multiple times for each element on the left. You've now simulated a list comprehension or an array comprehension. Asynchronous wait. You've got code on the left that will start running now but won't finish until much later, and you've got code on the right. Wait, it's sounding a lot like callbacks in JavaScript. You can just make this get registered in the scheduler to get called only once this operation finishes. Your future resolves, your promise resolves, whatever you want to call that. This is yet another overloaded semicolon operator you can now trivially apply across all of your code. And in fact, async and await have a history going back to work that was done in Haskell. Without adding any primitives to the language, we define a concurrency monad transformer in Haskell. This allows us to add a limited form of concurrency to any existing monad. The atomic actions of the new monad are lifted actions of the underlying monad. Some extra operations, such as fork to initiate new processes, are provided. We discuss this implementation and use some examples to illustrate the usefulness of this construction. Object deterministic finalization, RIA. In C++, you can allocate an object on the stack, and when the scope is over, it gets closed. So an object, code on the left will construct an object. You will have the semicolon operator will call the code on, will let the code on the left, it always gets run. You've given that object. It will call the code on the right, and then whatever the code on the right did, it will first call the deconstructor that was returned for the object on the code on the left before returning, and now you've guaranteed that all of this code in the scope gets closed. I/O and side effects. So given the thought process of thinking about monads in all these different ways, Haskell has this awkward issue, which is that it's purely functional. You cannot make any changes to anything in memory other than you're given arguments, and you must, and given those arguments, you can operate on them, you can return them. So you can return your computed result, but you can't use any global variables. You can't have what's known as a side effect where you leave behind state. But I/O is inherently a side effect where somebody is going to give you text that's coming from nowhere, essentially. You're going to be outputting text, and that text that you've outputted could go into something that has state. It could allocate bicycle messengers to go off and accomplish goals and then return back information. Haskell thought this through and decided that what you could do is you could make it so that code that has side effects will occur strictly in a particular order that can never go back in time and go into a different order, because we're going to take the entire world and pass it as an argument to a function. And then it will return the world plus the modification having been done to it. And if we can then do it all entirely within our overloaded semicolon operator, where the world is passed in as an argument and is essentially state that it threaded through. We're the only way to call the code on the right, because of its type signatures, to give it to this overloaded semicolon operator. You can make it so that this I/O is something that's now possible. And this is a wrong explanation. I'm not anticipating that necessarily you got that, but that maybe now you can go and learn Haskell and start seeing why they were doing some of these things and start learning it. I love looking at that language because it has like 2 syntax primitives, and it gets all these features and you can add new ones. Whereas other languages, they're like, oh, I'd like to add exceptions. Well, that will take a very long time to figure out how we're going to add exceptions to this programming language. It's like, no, that's like 4 lines of code in Haskell to add exceptions, whatever you'd like to do. Erlang, robustness and true fault tolerance. I'm not saying correctness. I'm not saying learn Rust for correctness here. I'm saying it's very different. So Joe Armstrong, the guy who invented Erlang, said this, something very interesting. This is a central question I hope to answer in this thesis. Large systems will probably always be delivered containing a number of errors in the software. Nevertheless, such systems are expected to behave in a reasonable manner. He didn't actually go for correctness. He was just like, the system is going to be incorrect. Let's make it work anyway. He then had a premise that error handling, fundamentally, in the Erlang view of the world, is non-local. This statement about error handling is perhaps less obvious than other statements he had made. When we make a fault-tolerant system, we need at least 2 physically separated computers. It's like, why are you even programming if you don't have 2 computers in mind? Like, it's never going to work. Using a single computer will not work. If it crashes, all is lost. The simplest fault-tolerant system we can imagine is exactly 2 computers. If one computer crashes, then the other computer should take over what the first computer was doing. In the simple solution, even the software for fault recovery must be non-local. The error occurs on the first machine, but is corrected by software running on the second machine. He felt that you really just needed to let errors happen, have them completely fail to whatever component, and have other components that were as disconnected as possible to fix them. The Erlang philosophy for handling errors can be expressed in a number of slogans. Let some other process do the error recovery. If you can't do what you want to do, die. Let it crash. Do not program defensively. And he built a system that was designed to isolate failures even within a single process, even within a single program, from being able to affect other parts of the system, and then made it so that you'd be able to notice when other components were just had totally failed and try to figure out what you were going to do at that point. Which is very different from the error handling philosophy of Rust, which actually kind of irks me sometimes. We all write code differently, but error handling is usually the last thing we want to think about. This isn't great for the overall design of a program, but it can be useful for rapid prototyping, because Rust forces us to be explicit about error handling by making us call unwrap. It is easy to see which parts of a program can cause errors. You imagine like Joe Armstrong and the person who wrote this getting into a big argument over the idea that you should ever even think about errors, much less try to handle them. Esoteric languages. They're fun languages that are like trying to program with one hand tied behind your back. This is a programming language. This is a program written. I'm not going to read it. This is a program written in a programming language called Chef, which is the idea is you've got a bunch of mixing bowls and you've got different amounts of different ingredients, and these represent different variables you've got going. And the challenge is, can you make a program that both prints Hello World or does Fibonacci sequence, and that if you handed it to a baker and actually had them executed in a kitchen, would construct a tasty dessert. And so this was Hello World cake with chocolate sauce. Please do not fear forgetting. I've talked to people who like, well, I could learn more languages, but I'm really concerned that if I learn more languages, I'm going to forget the languages that I already know. And I think that's not really. There's this thing, first of all, called code switching, where people actually they'll when given it back in another context, the language will come rushing back to them, and they will almost feel themselves forced to speak it. And sometimes it can be difficult to remember, like, oh, I'm speaking something in my family, and actually, but I'm in a context where everyone should be speaking English, but my family members all speak normally Spanish, and like I actually now have to put forth myself in a different thought context there. I have a friend who does this with QWERTY and Dvorak, where they will like switch back and forth between, they had an issue with a keyboard mapping. Their web browser was in QWERTY and everything else was in Dvorak, and they would actually just task switch and just type in the other one. There's a book called, another compromise here, there's a book called The Loom of Language, which was written by linguists back in like the 40s, and they had this premise that the more languages you can try to like learn, you can actually like learn essentially the like meta languages and the history of languages, and it can be easier for you to come up with words that you might need, because they're actually oftentimes are very similar across languages. There's this concept called spaced repetition, which is that sometimes it's actually very important that you forget things in order to be able to remember them, that it's actually the recall process that is hard for you, not the storage process, and that if you make it easy to recall because you never give yourself time to have forgotten, it's like you're never really stressing the muscle of remembering something, and that it's actually a good thing to let yourself forget something just a little bit and come back to it. It's a concept of desirable difficulty. Forget to learn. I'll say that 10,000 hours of deliberate practice, this is another concept that's come up that has been largely debunked in some sense, because there's this idea that if anything you do deliberately practice for 10,000 hours, you will become an expert at. I think part of it is that practice doesn't make perfect. Practice makes permanent. And that what you really need to be doing is thinking very actively about what it is that you're trying to learn, and thinking through where your holes are. And it's not just even deliberate practice, but in some sense it's, in this case, letting yourself forget the things that you were doing wrong and then trying to not remember them later, such that you can activate the spaced repetition on the good parts and lose them from the bad parts. If you're going to fear anything, fear maintenance. Don't fear re-implementing your own work later, because you probably will do it better the next time, but please do fear re-implementing other people's work, because you probably don't know why they did what they did. That said, don't blindly accept anyone else's work, because other people's work oftentimes has made trade-offs that don't make any sense for what you're actually trying to accomplish. Avoid new and shiny, because new and shiny things honestly tend to lead to maintenance failures. That what ends up happening, you spend all this time working in the new system. The person who built the thing with the thing that was 30 years old, well, 10 years later, now it's 40 years old. It probably works just about as it did 10 years ago, whereas the thing that you started using today that came out yesterday might not even exist next week. Avoid junk learning. This is a premise that learning something is actually changes you, and that if you spend time learning things that are useless, that you actually, or that are bad, it can actually make you worse. And so I think a lot of the new and shininess also is somebody who had this great idea that didn't actually make any sense, and that after 3 years everyone realizes it didn't make any sense. And the more time you spend learning the thing that didn't make sense without knowing that it didn't make sense, the more you will end up doing things that don't make sense. I know somebody, though, who does this leapfrog strategy thing, where they learn the new thing so that they can access all the new technology that might be available within the scope of the new thing, and they do bleeding edge for a little while, and then they let themselves wait and use that technology until it is ancient, and then they leapfrog to something drastically. But I don't know if it's sane or not. Discover your own taste in software. This is something where I think it's very important. It's like if you want to be a poet and you're not reading other people's poems and deciding what you like or don't like about them, you're probably not going to be a very good poet. And this is Lisa Marie Basile, is an author of 3 collections of poetry, talking here about how important it is to read. Read lots of code. Read your own code. A lot of times you write code, you never go back and read it. I think the best debugging model you should be doing is to go back and just read your code over and over again. Every time you make a change somewhere, spend a little bit of time. Read through all your code. You might now have learned something new that will actually cause you to change things elsewhere. Quickly learn from your own mistakes. This is something that I think sometimes you make a mistake and then you accidentally learn it, and then you start practicing the mistake. If you don't fix your mistakes, you will end up getting stuck in them forever. But also learn from other people's mistakes. But before you do that, verify they actually made a mistake. Because sometimes they will write a giant article on a rant saying that something was considered harmful because it burned them that one time. But it wasn't necessarily that bad. Maybe this is not the greatest example, but GoTo is something where people were lashing out about it so bad that they were like, this code base has the GoTo word in it. They are clearly incompetent. And it's like, no. GoTo should be considered dangerous. You should be careful with it. There are cases where it is actually makes things clearer because there wasn't a built-in control construct that did what it was doing, that did what you were supposed to be doing. Care about your tools. And choose good tools. I mean, if you think about the person you know is the best chef that you've ever met, probably has spent really a lot of amount of time choosing a really awesome knife. And that might or may not be a really expensive knife. It might be a really simple knife that they can get anywhere. Your text editor is your personal decision. And I point this out because no matter how many times I've heard the premise that you're going to sit down with somebody else and they're going to have to understand your text editor, I've never seen that happen, because you can always just close it and open up the other person's text editor. But you are going to be living with this text editor forever. Customize it. I really regret not having spent more time when I first started text editing fixing things in my text editor that were bothering me. I'm like, this is 15 years that I did not spend with a slightly better text editor. Oh my God, why didn't I do that forever ago? What was I trying to prove? Does your laptop spark joy? I really like this size of laptop, and it is depressing to me that apparently no one else does because they've discontinued all of them. And I hate fans, but like I think through, like, look at all the different options and choose something that's actually got this conference. I guess there's probably only 2 options you can choose. They're just different sizes of the same one. Customize your tools. And I'm nearly done, by the way. So the concept of there's this, and Stargate, they essentially had the jailbroken Stargate. They had the Stargate without the little dial home device that would use like the little touch tone thing in order to make the Stargate open. So they attached this giant supercomputer to it, and it sometimes didn't really work all that well. And they kept trying to fix it, but it gave them internal access to how the Stargate worked, and they would be able to know when gates were opening well before, like, you know, the thing actually opened, and they were able to access details of the routing configuration of everything. Like, there's actually power to making, customizing, and working within tools that you are using constantly, so that you can, even if there's a little bit of weirdness about them. Sometimes pass -F, sometimes just force it. And like, if you know what you're doing, that can be okay. I've seen people terrified to ever do something the tool says you shouldn't do. Sometimes the tool did that just to make certain that you don't do it arbitrarily by accidentally. It's still fine to do. But try to prevent the consequences from your passing of -F. In one of the episodes in the first season of Stargate, they just passed -F, and they managed to force a wormhole through a sun. And that was really, really bad for everyone involved. Process itself is a tool. Spend time thinking about how you communicate with other people and what you do with task lists, to-do lists. I don't have any specific advice on that because you'll get into a giant argument with everyone about exactly. There's a really fun conversation we had yesterday morning about whether you should be using mailing lists, Slack configured in certain ways, whether you should be using. I've got this great idea where we use WhatsApp, and we've just decided that there is no knowledge transfer later. All sorts of different arguments, but they all got trade-offs, and just caring about that is important. Read the manual that came with the tool you're using, because you might not realize that there's actually this perfect command line argument that was designed just for you and that no one else is recommending because they don't use it. Read the manual again 3 years later if you're still using the tool, because now you've changed and that flag is now useful to you when it wasn't 3 years ago. Care about why people wrote tools. Read the mailing list back when they were working on building the tool in the first place, because that'll tell you the context the tool came from. Read the issue tracker with all the people who failed to use the tool. The marketing materials for this tool are great, but no one likes it. It doesn't work half the time. It doesn't do what I want it to do. You figure that out from reading the issue tracker. And therefore, I will say history is important. I gave an entire talk about this at the last 360 iDev. Try to avoid distractions. This is something that I've noticed people who are really good at something manage to block off time to do that thing. And if you don't block off time to do that thing, you're not going to succeed at getting good at that thing. Now, that's not to say that that's maybe not the thing you should be optimizing for in your life, but that's not the best thing to be doing at all times, but that's something that for the particular aspect of improving in this way. Use music knowingly then. So music can also be a distraction. It's a distraction maybe from the drudgery of the thing that you're doing. But there was a great study that showed that, so they had groups of programmers, and they gave the same task to all the programmers. The people who were listening to music did it just as fast as the people who didn't. The people who were listening to music were happier at the end. That is true. The people who were listening to music did not notice the fact that the problem reduced down to return the argument. There was a bunch of math that all canceled out. The people who didn't listen to the music, a bunch of them actually figured that out. There's like a part of your brain that's busy processing the music that is not thinking about what you're doing, and it's letting you just coast along. Be careful. But it's a trade-off. I mean, it certainly can make you happier. That's important. Soundscape. I've actually found it something, if I've listened to the kind of music that I was listening to while I was working on this project, the last time I was working on it, suddenly the memories start flooding back to me about how the decisions I made while working on it. Generally I'm not even rushing. I just did not. I think you should find force multipliers, but I don't have a story related to them. I think you should try to find things that manage to improve the things that you're doing in ways that like when you think about something, decide, will this make me more powerful or will this be a drag on me in some way? So it's not about allocating time for self-improvement, it's about investing time in self-improvement. And that's it.